let's get started. Again, I want to remind that homework night is due 10 next Tuesday, okay? And then for you guys are having lab this afternoon, we are doing momentum and collision. Again, I'll just remind you guys to bring your face shield. If you have to be face to face, then you want to put on your face shield, okay? Um, then exam 3 is scheduled next Friday for Friday's lab attendees, and then Monday after that for the Wednesdays lab attendees, okay? Um, so today's classroom disinfection I assigned to Austin and Ethan. Okay, all right. So last time we started this chapter 10. So we'll have a quick look. So basically we talk about angular oscillation. Let me see if I believe I'm not muted, but let me just double check. Okay. So angular oscillation is defined as change in angular velocity divided by change in time t. Okay. And now for the oscillation, so if an object is having rotational motion, so that means it will have a centripetal oscillation. And then at the same time, if the angular velocity changes, then you will have also expect a tangential oscillation. So then there are two components for the oscillation, okay? Tangential component and oscillational or centripetal component, okay? So that's the overall oscillation. And we talk about kinematics of rotational motion. So basically, equation of motions for angular motion or rotational motion, they are similar to what you had in linear motion. Okay, so basically you just change the quantities there. All right. Today we'll check on the next a couple of sections here. So first, let's take a look on this bicycle wheel over here. Okay, so if you give the force, then the bicycle wheel will rotate. So that means its velocity changes. So that means you apply, you give it an angular oscillation, right? So because of the force, okay? Now you can keep your force. You can move the action point of the force closer to the axis. So say if you are applying the same force on one of the spokes there, but closer to the axial, okay, and then you'll figure that the change in oscillation or change in velocity of the bicycle wheel is probably smaller. So in that case, the angular oscillation is smaller. So you can see angular oscillation, it depends on the force. It also depends on where your force is applied, the distance from that force to the x rotation, right? So there are two quantities deciding the angular oscillation. We'll take a look from the original linear motion equation of the Newton's second law, F equal to m times a here. Starting from there, so A is the tangential oscillation. It's equal to R times alpha, okay? So then F equal to mr times alpha. Now, if you apply both side equation by R, where the R is the distance from the action point of the force to the x rotation, okay? So then that gives you R times F equals to mr squared times alpha, okay? If you have a point mass like this guy over here, all right, in this case, we know on the left-hand side equation, R times F, if R and F are perpendicular to each other, then that's torque, right? On the right-hand side, you have mr squared times alpha, okay? So you have a quantity that is angular oscillation, and then in front of it is a term called mr squared, okay? Now we say that torque is the analog of force in rotational motion compared to the linear motion, and then alpha is the angular oscillation compared to the linear oscillation, right? So if you compare this expression with the Newton's second law in the linear motion, so you figure that this quantity then will be the analog in the rotational motion to mass in the linear motion, right? So this m times r squared is called the rotational inertia or moment of inertia of the point mass over here, okay? So that's equal to mass times r squared. R will be distance from the point mass to the x rotation. All right. So this new quantity, we use I as the symbol for it. Okay, and then it should have an SI unit of kilogram times meter square. Kilogram times from mass, meter square comes from the R square. Okay. If you have multiple point masses, a few of them, then you'll just do summation of MI, RI square. Okay. Just add them up. So similar to mass, mass was when we talk about mass, it was the measure of the inertia of the object. So then this is the measurement of the moment of inertia of the object. So that means if you apply certain force, depending on this quantity, if this is large, then it's not as easy to make it move as if this quantity is smaller. Okay, so the smaller of I, you will get, you will have the larger angular oscillation. Okay. Moment of inertia depends on also the mass and then the distribution of mass. So that means the R, the distance from each of the mass to the x rotation. Okay, so that determines the moment of inertia of two quantities there. Okay. If you are given in a problem, if you are given a like regular shaped object, then the moment of inertia for the regular object can be found here. Okay, so again, it depends on the mass, it depends on the mass distribution, or we can put this in this way. It depends on where your x rotation is. Okay, because x rotation then defines the distance of each part to that x rotation, the r. Okay. So for a ring of mass m, then it's m times r squared if x rotation is through the center here. Okay. For a rod like this is 1/2 mr squared if you have x rotation going through the rod here, center of it. Okay. Now it depends. If the x rotation over is going through perpendicular to the rod here, then moment of inertia is different. Okay. So and then also this guy here. Okay. All right. And like spheres, solid spheres, okay, and then this guy is the shell. Okay, so different shapes will have different moment inertia from this table. So you can look up from this table to see what the moment inertia for a particular object is. Okay. All right. So then the Newton's second law in rotational motion, we can write it in analog to the second law in linear motion. So then we can write that tau equals to moment of inertia times alpha. Okay, so tau is equal to I times alpha. All right, so let's take a look on the first example of the day here. So it says, suppose you exert a force of 180 newtons tangential to a point 280 meters radius, 75.0 kilogram grindstone. You consider it as a solid disk. Okay, so let me see. So if you have a grindstone, it's going to be this is a solid disk like this, right? So then the x rotation should be going through the center perpendicular to this plane. Okay, so this is your x rotation. We can go a couple slides back to find what would be the moment of inertia of this guy. Okay, so it's a disk, right? And then with the center of rotation going through, x rotation going through the center over here. So it's like something like this guy, solid disk or solid cylinder, right? Cylinder or disk about this cylindrical axis. So then it's going to be equal to 1/2 mr squared. So this guy, okay? So I is equal to 1/2 mr squared, okay, for this guy. So let's go back to the problem. It tells you the R is 0.28, so R is 0.280 meters. Okay, and then it tells you the mass is 75.0 kilogram. All right. So it says a force is applied. So that's assuming it's going to be in this direction over here. This is where the force is applied. That's 180 newtons. Okay. Tangential. So that means if this is R over here, so this and this are perpendicular to each other. Okay. Let me see. All right. So this is R. All right. So it's asking what's the torque exerted and what's the angular acceleration assuming negligible opposing friction. Okay. So then this is the only force you will be considering. What's the angular acceleration if there's an opposing frictional force? Okay. So I think I'll give you guys a couple minutes to see if you can solve this one, and then we can take a look at the solution together, okay, in a few minutes here. All right. So let's take a look here. A is asking you what's torque. Okay, so in this case, torque is equal to R times F. Okay, because they are perpendicular to each other, R and F. Okay, now the full expression should be RF sine theta, right? If you remember, in this case, theta is equal to 90 degrees. So this is 90 degree. Sine theta will be 1, right? So this is 1. But just remind you guys, the general expression is RF sine theta, where theta is the angle between F and R, okay? So then this is 0.280 meters times the F 180 newtons, okay? I think it's kind of straightforward over here. So this is equal to 50.4 Newton times meter, okay? So that's part A. On part B here, it's asking you what's the angular acceleration, okay? So to solve for angular acceleration, you probably turn to the second law for rotational motion. So this is I times alpha equal to torque, okay? So then alpha is equal to torque divided by I, okay? We have the torque here. We need to calculate what's I. So you can calculate I first. I is equal to 1/2 mr squared, so 1/2 times 75 kilogram times r squared. Okay, that gives you 2.94. That's in kilograms meter square. Okay, so then your alpha is equal to the 50.4 divided by 2.94. All right, so that would be 17.1 radians per second square. Okay. And part C is asking you now if we consider the friction, okay, so the friction it says is like 20 newtons exert 1.5 centimeters from the axis, okay? So you can imagine it's going to be somewhere here going in that direction F, and then this is 1.5 in centimeters, okay? So then you have two, you have torque, net torque by this force and this force, right? So you have to recalculate your net torque, okay? So in this case, then net torque is equal to the R times F minus this guy, all right? Let's use small r as here. Now it's going to make this grindstone rotate in the other direction. So minus small f times small r, okay? So R times F is the original net number. You can just take that number down minus the 1.5, that's in centimeters. So convert it into meters and then times the 20 newtons, okay? So that reduced this guy a little bit, okay? Not too much because that's a smaller force and then exerting at very close to the same x rotation, okay? So that's just reduced a little bit, okay? This case, your alpha is equal to now the net torque divided by moment of inertia. Okay, so 50.1 divided by, again, that moment of inertia or rotational inertia. So 17.0, just reduce slightly. Okay. All right. Let me know if you have any questions. Okay. All right. So if you guys are clear, we can move on here. Okay, so we kind of check on the second law for rotational motion. So if you remember when we talk about linear motion, the next thing we check was work and energy, right? Or work first and then energy later. So here we will do the same for rotational motion. We will start with what the work is defined in linear motion. So it's defined as F times the distance traveled, okay, delta S, or D in that sense. But here, because for the rotational motion, the distance traveled should be the arc length. So we'll replace the D with delta S, okay? And arc length is equal to radius times the angular displacement theta, right? So then that gives you F times R times theta, because delta S is equal to R times theta, okay? Now you can see F times R or R times F, that is defined as torque. So then in rotational motion, work is equal to torque times theta, okay? Theta will be the angular displacement, okay? So should be, you can make it delta theta to be more accurate, okay? So just notation, but that means the angular displacement, okay? So work equals to tau times theta. So torque times this guy, okay, in rotational motion. And then we are assuming that at any moment, R and F are perpendicular to each other, okay? All right, so let's take a quick a look on the one of the simple example here. So this one says, if you are turning a doorknob through a 0.25 of a revolution requires that much of work. If the action point of the applied tangential force on the doorknob was 2.5 centimeters away from the X rotation, what's the force required to turn the doorknob, okay? So you can assume this is the doorknob, right? This is where you apply your force, tangential force. And then this is the radius of the doorknob, where it's 2.54, okay? 2.54 centimeters is the R, this guy. You're looking for this force, okay? And it tells you work is equal to 0.14 joules, and theta or delta theta is 0.25 revolutions, right? We just learned that work is equal to tau times theta, okay? And then tau, the torque is equal to R times F, right? So then this is work is equal to R times F times theta. And you're looking for theta. No, you're looking for F. Okay. So then you can figure that F will be equal to work divided by R times theta, right? You just divide both sides by R times theta to isolate F, okay? So it'll be like 1.14 joules divided by R, the radius, 2.54. Now this is in centimeter. Again, you want to pay attention to the units, okay? So convert it into meters there. Theta is 2.25, that's in revolution, right? Revolution is not the SI unit for the angle, but radian is. So that means times 2 pi to give you radians, okay? So a couple conversion there. Then force is equal to 3.5 newtons, okay? On this guy. All right. So next we'll check the work energy theorem here, okay, in this case. So similar to what when we check work energy theorem in linear motion, we start with the equation of motion, the last equation of motion there, v squared equal to v0 squared plus 2a D in that case. But this time, because we are in rotational motion, so we'll look at W square angular velocity square equal to initial angular velocity square plus 2 times angular acceleration times theta. Okay. And in combination with the second law, now this time in the rotational motion. Okay, so you will rewrite from the second law that alpha equal to tau over I, and then replace alpha with this expression of tau over I. So then this equation becomes this guy. All right. And from there, a couple steps of algebra. Okay, let me show you on the paper here. So basically, from this omega square equals to omega square 0 square plus 2 tau over I theta. Okay, what you want to do is multiply both sides by I. Okay, then you'll have I omega square equals to I omega 0 square plus 2 tau times theta, because you distribute I into the two terms inside the parentheses. Okay, and then move this guy to the other side of the equation. So you'll have I omega square minus I omega 0 square equals to 2 times tau times theta. Okay, because tau times theta is the work W, right? So you further isolate work from the other term. So divide both sides by by 2 or multiply by 1/2. So multiply by 1/2, that means the first term you multiply by 1/2, and then second term you also multiply by 1/2 to get rid of the 2 here. Okay. So then you arrive with this equation over here. So 1/2 I omega square equals to 1/2 I omega 0 square equals to tau times theta, which is work. Okay. So then you have 1/2 I omega square minus 1/2 I omega 0 square equals to work. This equation over here, right? Now remember, in linear motion, we had like 1/2 mv squared, right? Well, minus 1/2 mv0 squared equals to work. Okay, so these two are very similar to each other. You only replace the mass, the analog in rotational motion, which would be I, right? The moment of inertia. So then this is its analog in rotational motion, and then this is the velocity in angular motion or rotational motion. So similar to this guy. So 1/2 I omega squared minus 1/2 I omega 0 squared, right? In linear motion, we call this term as kinetic energy of the linear motion. So then in rotational motion, we also call this as kinetic energy in rotational motion. Okay, so this is also the kinetic energy, but in rotational motion. Okay, so that means kinetic energy, rotational kinetic energy in final minus rotational kinetic energy initial is equal to work done in the rotational motion. Okay, so this is then the similar statement for the linear motion. Okay, so work energy theorem in rotational motion here then. All right, which is defined, rotational kinetic energy defined as 1/2 I omega squared, and then similarly work energy theorem apply here. So work equals delta K. Okay, work equal to change in kinetic energy, or work equals to kinetic energy final minus kinetic energy initial. Okay. All right. Then let's take a look on the next example here. This one says when a pitcher throws a curveball, the ball is given a fairly rapid spin. If a 0.15 kilogram baseball with a radius of 3.7 centimeter is thrown with a linear speed of 48 meters per second and an angular speed of 42 radians per second, how much of its kinetic energy is translational and how much is rotational? Okay, So in this case, you can see the baseball has linear motion, right? It has a linear speed as well as a rotational motion because it has spin, okay? So then the kinetic energy should be combination of both linear or translational kinetic energy plus the rotational kinetic energy, right? So there are two parts here. All right, and then you are looking for each of this kinetic energy. So you can see the baseball, it's going with a linear speed, 48 meters per second. At the same time, it's rotating. So let's say this is rotational. It says 42 radians per second. Okay. Now it says assuming the ball is a uniform solid sphere. Okay, so the moment of inertia is not given, but it says it's uniform solid sphere. So then you will again just look it up in the table for the moment of inertia. Okay, so we are looking for a solid sphere, uniform solid sphere. Okay, so then this is the solid sphere. Okay, about an any diameter. So it goes through the diameter here. All right, X is going through the diameter here. So then I is equal to 2/5 mr square. Okay, so for a solid sphere, it's 2/5 mr square. Okay, so you can write that down for your moment of inertia. I for the ball is 2/5 mr square. All right. It tells us R, it tells us the mass. Okay, so you can calculate this guy. So then kinetic energy, let's see, if you say T, that means translational or linear. So that would be 1/2 mv squared, right? Kinetic energy, if you say R, that means rotational motion, 1/2 I omega squared, okay? You can basically calculate this too, okay? All right, so let's see. KET 1/2 m, that's the given as 0.15 kilogram, 48 meters per second square. Okay, so that's 173 joules. Okay, for translational kinetic energy. Rotational kinetic 1/2 I will take 2/5 mr square. Let's keep the capital M here. And then times omega square. Okay, it tells you the omega here. So 1/2 2/5 0.15 R is given as 3.7. Okay, again, this is in centimeters, so convert it into meters, square it, and then the 42 radians per second square. Okay, so it turns out this is actually much smaller than the translational kinetic energy. Okay. The 42, yeah, radians per second is the omega, the angular speed. So rotational kinetic energy is 1/2 I omega square. Okay, omega is the angular speed. Okay, so that's 42 radians per second. All right. Okay. All right. So let's see. So the baseball, it has spin, it has linear speed as well. Okay, so in another scenario, okay, so an object could also have linear motion and rotational motion. So for example, the bicycle wheel, if it rolls from one point to the other point, okay, so when it rolls without slipping, okay, so then that means so this is what happens here. Okay, so then you can see the bicycle wheel has, if after a certain time t, you can see it moves from one place linear to the other place, right? So then there's linear motion here, and then also there will be rotational speed because it will rotate with the axis going through the center of the wheel. Okay, so both cases. In this case, the linear speed v is equal to 2 pi times r if we take one period. Okay, here. So then, because it's not slipping, so then at the contact point over here, right, it's not slipping. So it actually has a relationship of this linear speed equals to r times omega. Okay, so this is the general relation if an object is rolling. Okay, of course it has to be like a circular object or spherical object. Okay, so then that's the relationship between the linear and rotational speed. Now, if the object is slipping, then this relationship doesn't apply. Okay, so in the case of the baseball, it spins, but it's not rolling actually. So then the angular speed and linear speed doesn't necessarily have this relationship. Okay, this happens when you are just having the object rolling without slipping. Okay. All right, so let's take a closer look here. If object is rolling, then its linear speed or linear velocity at different parts of the object actually is different, right? Because for example, the overall motion is the combination of the linear motion and rotational motion, right? So this is the rotational motion, this is the linear motion. So if you look at linear motion only, then this velocity at any point is the same, right? If it's just a linear motion, not without any rotational motion. But for rotational only, the velocity actually at different points are different. So say here is to the right, right, with v equals to r times omega. over here it should be to the left, right? So these two are in the opposite direction. You can indicate if this is positive, then this will be negative, right? Now the overall motion for a bicycle that is rolling will be combination of this one and this one, right? So then on the top here, the velocity from rotational motion plus the velocity from linear motion will add up, okay? So then overall on the top here, it's going to be twice of r times omega, right? At the center here for rotational motion, this v will be equal to 0 because r is equal to 0, right? So then at the center here will be just the linear motion velocity v equal to r times omega. At the contact point over here, then things is very interesting here because linear motion has a velocity to the right, rotational has velocity to the left with the same magnitude. So then at the contact point, v is equal to 0, okay? So when you have a wheel or a tire that is rolling, at the contact point, actually its overall velocity is equal to 0, okay? That's why when we talk about the friction force in this scenario from the ground to the wheel or the tire, it's actually static friction, okay? So in that sense, static friction is good because then static friction actually provide the force pushing the wheel forward, right? Just like when we are walking, so we are pushing the ground backward, the ground is pushing us forward. That's static friction, okay? Because in the contact point, your shoes and ground is not having relative motion, right? It's static friction. In the same scenario here, the tire and the ground is not having relative motion, so it's static friction, okay? Now, if it's slipping, then it will be kinetic friction, right? That's relative motion then, okay? All right, so then for a rolling motion, because the object is rotating and then also having the linear motion, so then overall, our total kinetic energy, you should consider both the linear or translational kinetic energy as well as the rotational kinetic energy, okay? So it's 1/2 mv squared plus 1/2 I omega squared, all right? And then for a rolling motion, you have a relationship of v equal to omega times r, or omega equals to v over r, okay? So then you can rewrite this total kinetic energy as so I think there's a 1 or 2 steps missing here from here to there. Okay, so let me just show you what's missing there. So you basically are going to write, so k is equal to 1/2 first term mv squared plus 1/2 I, that'll be v squared here over r squared, right? Because on the top there, when you are doing v over r squared, you square the top and then do square the bottom here as well, okay? Now, you want to rearrange or modify this term a little bit, okay? So you can do this, you can multiply it by mass divided by mass, right? Basically, it doesn't change it, but you're going to change the expression of it slightly, okay? So then this becomes 1/2, you can put 1 mass in front here, v squared, right? So you have mv squared, and then you are going to write the remaining terms over here. So it's going to be I on the top remaining, and then in the bottom you have mr squared remaining. Okay, so you can rewrite this term by multiply by m over m, which is 1, right? Doesn't change the result, but rewrite the terms. So then k equals to 1/2 mv squared plus 1/2 mv squared times that guy, right? So then you'll single out the 1/2 mv squared. The first term will be simply 1/2 mv squared times 1, right? So then it becomes 1/2 mv squared times 1 plus I over mr squared, okay? So your kinetic energy is then this expression, okay? Which is the multiple, so this is a multiplier, right? To the translational kinetic energy. 1/2 mv squared is your translational kinetic energy with a multiplier, okay? So that's your total K total. All right. So in that case, so if you have an object that is rolling down a slope, okay, so then because it's rolling down, so then the friction between the object, so for example, if it's a sphere here, the friction between the sphere and the slope over here is static friction, right? Static friction does zero work because there's no relative motion, okay? So then friction doesn't do any work here, then normal force will also do zero work because normal force is perpendicular to the motion, right? Or to the surface of contact, which is the motion, direction of motion. So the only force that is doing work would be the gravitational force in this case, okay? And gravitational force is a conservative force, so then you can apply conservation of energy. So for a rolling motion, the energy conservation will apply, okay? So then let's see here. If that's the case, okay, we are going to take a look on this. So if that's the case, then you will write that kinetic energy plus potential energy initial is equal to kinetic energy final plus potential energy final. All right. So kinetic energy initial, the object is at rest, right? And then rolls down. So then kinetic energy initial should be 0 plus potential energy will be mgh, right? So from here, you can take this as your ground level, the lower point over here. So mgh, all right? And then final kinetic energy would be 1/2 mv squared, right? Total is 1 plus I divided by mr squared in the previous slide, right? Kinetic energy total, because you have rolling motion here, plus final potential energy will be 0. We take that as the reference point, ground level. Okay, so then you can solve for V here. You can see that mass and mass will cancel out. So then V, to solve for V, you can move this guy to the other side of the equation. So that means GH divided by this term, right? 1 plus mr squared equals to V squared. Okay. So then for V, you take square root, of that. Okay. So at the end, your V should be equal to square root of GH over 1 plus, should be 1 plus I over mr squared. Okay. So that's your final speed at the bottom of the slope on the slide. Okay. All right. So in that case, then if you would compare two objects rolls down the same slide, if they are having the same mass and same radius, for example, if you have a disk, you have a ring. So then the question is which one will reach the bottom first, right? So for the one reach the bottom first, that one should probably have a larger speed at the bottom, right? Because then the overall velocity will be larger. So then it will reach the bottom first, okay? So then you'll be looking at this and see which one will give you larger speed, okay? Because everything else is the same. GH1 is the same. MR squares is the same. So you will be just really comparing the I, right? So if you have a larger I, then this denominator will be larger, right? So then the speed will be smaller, okay? Or in that sense, you want, if you are looking for which one is reaching the bottom first, you want to have the one has the smaller I, right? So then you're looking for which one has smaller I here. So for a ring, I of a ring is equal to mr squared. Okay, I for a disk is equal to 1/2 mr squared. Again, these two moment of initial, you can look them up in the table, the figure table earlier in the slides. Okay, so you can see the disk will have smaller moment of inertia, right? So this one has smaller moment of inertia. So that means velocity will be larger. So the disk will reach the bottom first, okay, in that sense. All right. Okay. Um, so I wanted to take a look on this example with you guys, but it looks like we don't have enough time for it, okay? So I think we'll come back to this one on Monday, but you guys can try to do this after class, okay? And then on Monday we can come back and then just check on the solution together, okay? So I think we'll just stop here for right now, okay? All right, see you guys in lecture on Monday then. Sure. Hi. Yes.